Hello everyone. We've been talking about the weighted least squares method. Now, the first case that we've been seeing is where we assume that we know the form of this heteroscedasticity and we know it up to a constant, a multiplicative constant. In other words, the heteroscedastic variance, right? Variance of ui given xi, we're able to express that as a function of the x variables. And in particular, we're calling that sigma square times h of x or sigma square times hi. And we assume that we know the form of this hi. So in the earlier case, when we saw a savings function, we assumed that hi just takes the value income I, inc sub I. So we assumed that there was a linear relationship between that the variance of the error term was linear in income. Now, that's a very arbitrary way of coming up with this functional expression, right? We assume that the variance in the error terms was linear in income, but what stops us from assuming that the variance is quadratic? So the underlying assumption here is that when you're trying to come up with this expression or form of heteroscedasticity, there is some level of arbitrariness there. Now we're going to review a very special case where the way in which we assign these weights, the way in which we assign this hi function actually arises naturally from the way the econometric model is constructed. We're going to look at a very special case here. So this often happens when you have data that is reported as averages rather than actual numbers. So for example, let's look at a model where we're trying to model the pension contribution of employees. So there are E employees, and let's say we have I different firms. So every employee's contribution is modeled as a function of how much money they're earning. Contribution to their pension fund is a function of their income, their age, and the M rate variable gives us the contribution from the company to the employee's pension fund. Okay. So suppose this is the individual level model, where every row in the dataset pertains to a given employee who belongs to some firm. Now, suppose we assume that this model satisfies our assumptions 1 to 5, MLR 1 to 5. That means these error terms here satisfy the assumption of homoscedasticity or constant variance. But suppose we have data only on averages at the firm level, meaning we don't have information on every single employee in a given firm, but rather we only have the average values for each firm in our sample. Average employee contribution, average employee income, average employee age, and the average contribution from the company. So we only have averages at the firm level, so we have to run a regression only at that firm level. Now, we don't know if the error term here is homoscedastic or heteroscedastic. But turns out, because U bar is just an average that comes from UIE, and we know that the individual level model is homoscedastic, so we may, just the way in which the model is structured, it helps us find the weights for our WLS model. So let's see how that works. If the individual model satisfies all the 5 assumptions, the first 5, then the error term in the first case can be modeled this way. The variance of the errors there is a constant sigma square. And MLR4, which is that your E of u given x is 0. The errors don't depend on the value of the x values. Or in other words, we can say that the errors are uncorrelated across employees within a firm. So for another way of just saying E of u given x is 0 is that your errors across units or between units, they are uncorrelated. So if those assumptions hold, how do we write down the variance of U bar? Well, U bar is nothing but the variance in the average model that we are running at the firm level. So variance of U bar. So suppose we assume that there are MI employees in firm I. Okay. Then U bar I is just sigma u over the number of employees in that firm, right? Which is what we're doing within this bracket here. So this expression, variance of 1 over m times this sigma times ui, it just becomes 1 by m square times variance of sigma times ui. And this just becomes 1 over m square into sigma. E goes from 1 to mi times variance of ui e. So you just interchange the sigma and the variance terms. So you're left with 1 over mi square times mi times sigma square. So variance of ui is just sigma square. And if I'm just summing that for m different values, I have m multiplied by sigma square. So this is nothing but sigma square over mi. So now we've been able to express the variance of u bar as sigma square over mi. And you have to compare and contrast this with, so generally we try to write the variance of ui given xi in this form, right? Sigma square times hi. And then you have, so if you were to compare and contrast these terms, your hi is now 1 by mi. Or we can say that 1 over hi is equal to mi. So in this way, just the number of employees, a functional form of that becomes our weight in the WLS model. So just the way in which the model is run, just because we're running the regression at the level of averages, this helps us get to the weight, the hi term very easily. And we don't have any level of arbitrariness in how we define those weights. So this is just a special case. If the but of course, we were able to do that because we assumed homoscedasticity in the individual level model. If we cannot assume that, then one way of working around this is to do a WLS model, a weighted least squares model. And once you run that model, you can ask your software to give you robust standard errors on that weighted least squares model. So that's just another way of making your results more foolproof to this heteroscedasticity problem, and that is often done in practice. So this wraps up the topic for this particular video. In the next video, I'll talk about something called the feasible generalized least squares model. See you there.